Okay, here's another example for you. In this one, we are going to start with wavelength. And in light of the holidays, I decided to make it orange. Orange can have various wavelengths, but according to my friend Google, can go all the way up to 620. So we have a wavelength of orange light that is 620 nanometers, which is what the little nm stands for. And we want to find the amount of energy. So the amount of energy that light has. Or sometimes they'll ask this question, the amount of energy in the transition, which is just how much energy the electron jumps up or down to. That's the same thing. You're still looking for energy. So no matter how they phrase energy, just remember you're going to energy, and it's the same deal. All right. So we've got a couple problems here. Let's see. Well, first thing is wavelength is lambda. Energy is E. If you remember, we do not have an equation that has both of those variables in it. So this is what we're going to have to do. We are going to go and take our first equation that includes lambda, which is the speed of light, times wavelength or lambda, times frequency or nu. So this equation, and we need to solve it for frequency. And then we will then take that frequency and plug it in to E equals Planck's constant h nu. So we'll bring it over here and plug it in with Planck's constant, what we already know, and that'll be our second equation, and then I'll solve for energy. So let's get started with that. The first thing you're going to notice is that you have your wavelength in nanometers. You need to change that to meters. You can just do that in Google if you just forget, but when you have these 100, right, so this is a 620 nanometer, it just shifts. You put the decimal point right there, so 620 nanometers. Anytime it's 100 number of nanometers, so anything from 100 up to like 900, just put the decimal point in between there, so this equals 6.20, like what we've already done with scientific notation, times 10 to the negative 7th meters. And that's just a quick shortcut with that. If I recall, I don't actually give you a number in nanometers and force you to change it on the test. But you will see that a lot in the worksheets. So again, if you see it, you can either have Google help you out, or just remember it's a quick shift with putting the decimal. So it looks like scientific notation, and it'll be times 10 to the 7th. That just only works from 100 to 900. If you had like 1,000 something, it would be different. Or if you had like 99 or 89 or something like that nanometers, it would be a little different. All right, so now we have our wavelength. We need to change our equation around to solve for frequency. So it's going to look like this. Frequency equals speed of light divided by wavelength. So remember, you can have all versions of this written down on your periodic table if you don't want to be comfortable with the algebraic rearrangement that you need to do. Then we need to plug in our numbers. Again, you'll always have access to the speed of light on the board as a constant, but it's always the same number for us. It's going to be 3.0 times 10 to the 8th meters per second. So I'm going to go ahead and plug those in. So you got 3.0 times 10 to the 8th. My wavelength is right here. 6.20 times 10 to the negative 7th. And now with my calculator, I mean, you can't see my calculator, right? I mean, now in my head, I will do this because I have a giant head, and that allows me to do advanced calculations. Hopefully everybody gets that I am lying. To the 8th we got 6.20 to the negative 7th divided, and we get a frequency of 4.84 times 10 to the 14th. And frequency always has a unit of hertz. And as I told you in another video, you can also write hertz as 1/seconds. It's the same thing. Or actually, as though you need one more thing, you'll also sometimes see it as seconds to the negative first power. All of those are exactly the same thing. So if you see any of those, we will use HZ on the test. Okay, so now if you recall up here, we're actually going from wavelength to energy. We've just solved for frequency. Now we can put frequency into the energy, or Planck's equation, and now solve for the energy of that orange photon. All right, so now I am going to use E equals hV. Plug in my numbers. Remember, Planck's constant is always the same number, and you will be given it on the board, so you might have it off to the side. If you haven't already done it, you probably ought to just write it on your periodic table, so you can always reference that while you're doing your work. And the frequency we solved for up here, so I'm just dragging that down. And that will solve for our answer in energy. So now it's just a quick calculator. And a photon of orange light hitting you from your giant pumpkin you're carrying around to steal candy from children is going to have 3.21 times 10 to the negative 19th joules. 19th. I said 19th and I wrote 17th. 19th joules of energy. Again, always nice if you box your answer when you do your work. Helps me find it. And this is another one of your 6 problem types. This is a problem where you go from wavelength to energy.